Good morning, everybody, and thank you for joining us for another Power Hour Expert Mode. Today, we are going to be talking about distribution automation and fault location, isolation, and service restoration. Today, I'm Jeremy Anderson, and joining me today is Russ Fanning. Russ will be doing all the heavy lifting today, doing all the information about DA and Flizzr and some examples and some demo. So he will be handling all of that. As usual, if you have questions, use the question pane in your GoToWebinar toolbar. We'll try to answer those either live or at least get you answers back, and then all answers and questions will be provided after the webinar in our follow-up email. Usually takes about a week for that follow-up email to come out. Reminder, we are still giving away Power Hour t-shirts. So, you know, if you're engaged, all that, we try to pick 3, sometimes a few more to get and ship Power Hour t-shirts out to you as a little thank you for joining our webinar. And with that, I'm going to go ahead and turn it over to Russ, and he's going to handle it from here.
Very good. Let's see, I'm going to show my screen, and hopefully everybody can hear me okay. My name is Russ Fanning, and we're going to be talking about distribution automation today. I'm going to go through a number of things with distribution automation, exactly what is, what it isn't. We'll go through the basic DA applications that you can do with the DA logic out of the box, the way that it was designed to be used, including Flizzr and a few other advanced applications that you can still do with the basic DA. Then we're going to talk about the actual configurations of how to build the DA logic, how to put the inputs in, how to put the logic in for the sequential switching, and then going beyond that, we'll take a look at how you can enhance that to do some more advanced DA, including some of the things that I've developed over the years with others for some DA applications that were not even thought of when we started to develop the distribution automation. Okay, what is DA? To start with, distribution automation is not protection. There's been some confusion over the years of what protection does, what DA does, and are they going to fight each other? No, that does not happen. Distribution automation follows protection. Protection operates first. It does what it's supposed to do to stop the fault current from flowing, open up devices, and do the isolation that it normally would do. And then distribution automation looks at the system after the dust has settled and decides what the issue was, where the problem is, and start doing some isolation and restoration. I think there's a little bit of a difference in my description of Flizzr. I say it's fault location, isolation, sectionalizing, and restoration instead of service restoration. But both of them work for Flizzr. Okay, what defines distribution automation is you have to have automated devices that you can talk to, devices that you can send a control to open or close, devices that you can gather information from to be able to evaluate the system and make a decision as to what exactly happened and what are you going to do about it. This is a generic indication of what the causes of a feeder fault really are. A lot of it is tree growth, a lot of it is equipment failure, snow, lightning, wind, wildlife, all sorts of things that will contribute to an outage on the system. When you take a look at the breakdown of that as to where the faults actually occur, very, very few of the incidents will occur within the fence of the substation. Less than 1% of the outages actually occur inside the substation. But when they occur, they affect many, many customers. So that is one category. The secondary voltage system has lots of outages, but those are outages of service drop has broken, or a transformer failure, or a fuse blown. That usually it affects very few customers, but there are lots of outages. The bulk of the outages that contribute to the indices, the higher numbers of outage minutes that are used for calculating the feeder reliability, happen on the primary system. So roughly 40% of the outages contribute to about 91% of the customer outage minutes. And it's only the prolonged outages are the ones that are being used to calculate those numbers. We have three different categories. A momentary outage would be like a lightning strike, something that happens just for a second and then the power's back on. Something temporary would be an outage that is a prolonged outage for some, but might be restored through some kind of an automatic transfer, distribution automation, some equipment operating inside of a substation. And then you have the prolonged outages of something that is longer than 5 minutes. Those are generally measured by utilities using three different indices. The SAIDI, SAIFI, and CAIDI, which I'm sure that most of you are familiar with them. SAIDI is the measurement of the customer minutes, how the duration of the outage, and SAIFI is how frequently the customers have an outage. Those two indices are calculated from all the customers on the system that have experienced, that are part of that system, and the total number of minutes that are affected. Now, when you're calculating SAIDI, SAIFI, and CAIDI, that's on a system basis. That system could be a feeder. That system could be a substation. It could be an operating district, or it could be the entire utility. It depends on how you want to crunch the numbers. CAIDI is actually an average or a ratio of SAIDI and SAIFI together when you actually take a look at it. And when it does, when you do crunch those numbers, it really boils down to only the customers that have seen an outage of longer than 5 minutes are the ones that are used inside that calculation. The evolution of the distribution system over the last few decades has changed. In earlier days, back when I was first starting in the utility business, there were many small substations that had a low voltage distribution feeders coming out of them, serving customers in the neighborhood. They were being served from larger substations at a higher voltage that would go and feed that substation. There would be generally some kind of an automatic changeover either on the high side of the substation or on the bus of the substation that would transfer load if the source to that substation was lost. System conversions over the years have moved distribution systems to higher voltages. And when we removed the low voltage systems, feeders became longer. More customers were on a feeder, and we lost one level of redundancy at that high side automation changeover or the bus transfer schemes that provided a secondary source into those customers that were being served from that system. So distribution automation became a promise of how we are going to improve the system to provide the same level of reliability that originally was there when the distribution feeders were short with fewer customers. As a result, the longer distribution feeders get cut up into smaller zones that can be isolated by distribution automation, bringing the size of these feeder zones down to about the size of the feeders that were originally 4 kV, or at least with the same level of reliability. So from distribution automation being added to the system, that cuts up the distribution feeder so that the customer's perceived reliability is that the feeder that they are served from is no bigger than the zone that they are attached to. And hopefully, or by design, you are trying to get that zone roughly to the same reliability equivalence of what the lower voltage feeder was. When you apply DA, the flisser is going to be affected by DA. That is going to analyze the system, locate the problem, isolate the fault, and restore load. DA will improve SAIDI and SAIFI. However, CAIDI is most affected by the repair. So you have to get the right people to the problem, fix the problem, and get it turned back on. That is being done by your troubleshooters, by your construction crews. So DA can actually help that by identifying where the problem is, although DA cannot fix the problem if a transformer has failed, if a wire is down, if a pole is broken, but you can direct the manpower to the location of the fault to improve CAIDI. Okay, we're going to be talking about the DA logic now, actually jumping right into NCD. Everything that you need to know about configuring the DA logic is in the software manual that is a document that you can just get to from NCD using your link under the help to go to documents and pull up that information. By design, DA logic was intended to be substation based. You can use it in a wider area with one Orion being a DA controller that controls a wider area, but the ideal installation would be to run the DA logic for all of the devices that are being served out of one substation, and then having that concentrated inside that Orion. That makes the configuration files of the DA logic smaller because they're handling fewer devices. The system is simpler to configure, easier to comprehend. It just makes it easier all the way around. DA logic can run in the same Orion that your substation RTU is running. It does not have to be a dedicated second RTU or a second Orion, although there are some good reasons to run DA logic in a second Orion alongside the RTU if you choose to, which allows you to modify the logic that it's running in the DA system without affecting the operations of your substation and vice versa. DA schemes that are configured inside the DA logic are simply automated switching schemes, and it is intended to basically do the same switching operations that would be directed by a system operator at the control center if he were to punch a button and say open this distribution automation device and close that one. It's just the DA logic can make those decisions so much faster and accomplish what it needs to be done. But it is generally a scripted plan that should be thought out ahead of time. It is not intended to be a system that you simply build, these are the devices, go figure it out. There are other DA systems from other manufacturers that intend to do that. Many of the complaints that I hear about those systems is that it is inconsistent for the same kind of a fault. It will switch one day in one direction, and another day for the same fault, it would switch in a different way. That makes operating people in the field very uncomfortable with what is the DA going to do. It also is very difficult type of system to test when you have an unpredictable system like other systems outside of NovaTech. So they tend to be put in service with a trust me attitude that the software is going to work. The NovaTech approach is that it's a scripted plan that will always operate the same way. It gives control to the dispatcher, it gives control to people in the field, and we have, by design, safety mechanisms that are built into the software so that the DA will operate in a safe environment to protect people in the field. Here are the rules for what DA actually does, okay? When a fault is identified in the field, and by being identified, it's configured in the DA configuration as a piece of information to pay attention to. The DA system will stop doing the polling sequence that it is currently doing to all of the line devices in the field and in substation, and it will start a DA integrity poll. So it will start the integrity poll from the beginning to all of the devices that are in the DA system so that it gets a true vision of what the data is across the entire system. Once that is all gathered, then it will interrogate that data and find out where the location of the fault is or the problem, and then it will wait until we have both a fault indicator and a reclose input, a fault input and a reclose input. We'll talk about that when we get into the software. And when both of those are true, then and only then will DA start to operate. If multiple zones see a fault condition because fault current has gone through a breaker and a downstream recloser, maybe a switch, the one that is identified as being furthest away from the source is going to identify what zone the fault has occurred in, and that is the zone that will be used to isolate the fault and execute the sequential switching that will restore the power. Everyday devices that are put into the system Each device has a number of safety features, and one of the most important safety features is that a device will only be operated from its normal position to its abnormal position. So that means that a normally open switch can only be closed. A normally closed recloser can only be opened. It is not going to switch a device and then re-switch the device unless it is specifically coded to do that. And so that prevents the DA system from what I call chasing its tail, so that you don't have one DA event that switches to completion and then it is affected and undone by a second event. And then we have a number of safety interlocks that are controllable from SCADA or at the pole and in the field, that can temporarily disable a single device and partially disable the DA system, or permanently disable the entire system if chosen to. The three categories, or the three inputs that we have designed into the software to establish a safe work environment, is an auto manual control, a supervisory or local control, and what I'd call a programmable safety interlock. The supervisory or local remote switch generally occurs or exists at each one of the switchable devices, whether it is a pole top switch, a line recloser, or a feeder breaker. You generally have some way to say, I can control this from SCADA, or I can control it locally and block SCADA. That's what this control is. When it is in local, then any remote control command, whether it comes from DA or SCADA, will be rejected by that device, and that device will not be allowed to operate. The auto manual is a logical input, does not exist generally in the points of a switchable device. So that is a virtual point that is created in logic within the Orion using Logic Pack or using Lua or some other mechanism to be able to turn that on and off. You can use the same auto manual point for the entire system if you choose to, or you can have individual auto manual points for each individual device. And that will operate pretty much the same way as the local remote does. This is intended to be controlled either from an HMI or from SCADA. So that gives the control to the dispatcher to be able to go to an individual device, put it in manual, and just like putting the device in local, if you were standing at the base of the pole, DA will not try to operate a device that is in manual. The third safety interlock that's involved is a programmable local remote or programmable safety interlock. That could be any other input that you want to create. So that could be a hotline tag, which is often used for a line recloser, so that when it is in hotline tag, there's generally some crews working on the line in the field, and you want to leave the DA functional to an extent, but you don't want DA to close in on a crew that's working in the field. So that becomes part of your company operating practices, how you're going to do that and what you're going to do it with. Using those safety interlocks in combination, it defines what the device operating mode is. A device is fully normal if it is in auto and remote, not blocked by the programmable blocking, and it's in its normal operating state. When it's in remote, the local remote is in remote so that it will still accept commands from an HMI or SCADA, but it's in manual, the auto manual is in manual, so that DA will not operate it, but it still can be operated from SCADA under the direction of a dispatcher. We already talked about what local is, and limited is a special device mode that is determined dynamically based on the conditions of the system. Most of the time, a device is going to go into limited mode when there is a DA event or after the DA event has occurred. So if any of the safety interlocks are set, a device will be put in limited if one of these safety interlocks is in a restrictive mode at the adjacent device. So even though a device, let's say a switch, is in fully automated normal mode, if the next recloser down the road is put into local, the DA system recognizes that the next door neighbor is restricted and therefore puts this device into limited mode, which allows it to open to isolate a fault if necessary, but it is not allowed to close in limited mode. Here's some of the limits that you have to the DA system. You can build a DA system in one instance of a DA logic module with up to 512 devices, 64 zones, and the switched sequences number of steps that you can have is up to 32 steps in one zone. I have never gotten to the point of anywhere close to this in any of the DA systems that I've put in, and I've put in probably over 40 different DA systems around the world. When you get into configuring your DA logic, first thing you're going to do is open up your NCD, and when you navigate down to configuring the logic, DA is the DA logic underneath math and logic and so on. From there, you'll configure each one of these tabs. The first tab is called a port. This data update delay, I have it set to 20 seconds. I believe the default is 60 seconds. That you're going to want to set according to the equipment that you're using, and it's key about what kind of communications you're using. So if you are using fiber optic communications to a device on your DA system, and you're talking to everybody fiber, you're getting very good, very fast responses. But if you're using a slow radio system that's using 9.6 baud relay radio, then it may take a while to pull all of your devices and collect the information that you need from the devices. So you may want to have an update delay of closer to 60 seconds to be able to collect all of the information after a DA integrity poll, so that you have all the information that you need to analyze the system. This time is the amount of time that DA waits before it will start to analyze. So that is where that comes from. The other file parameter that's here, DA logic.log. DA logic will write a file with a step-by-step analysis and timestamp the actions that it takes. That is a file that is stored in the Orion, and you can download it from the Orion to analyze after the fact. It will continue for forever, actually. When it gets full, it will overwrite the existing file and create a new file. So it does not have a history forever. It simply fills up, and then it creates the last one. So after a DA event, you can pull that out of the Orion and analyze the system. One other thing that I mentioned earlier was in the safety interlocks. We have an auto manual safety interlock that has to be created as a virtual point. There's many ways that you can create that. You can create them in logic, and each one of those points that you would be a master auto manual at logic. If anybody is familiar with how the logic master protocol works. But there is another one called pseudo master that allows you to create devices and create points. And I'm not going to get into that, just letting you know that it's there. Look it up, and you can see how you can add devices. You may need to add a new device to be able to configure some special logic. And then once you have the devices created, you can create these points. One of the advantages of creating the points under pseudomaster instead of logic is that when it's done in logic, every single one of those points is going to be at logic. Here you can create a set of points for your auto manuals and call it DA auto, where my zone status is for keeping track of what DA sequence is being switched at the moment. You can create a set of points that are going to be the zone status that you use for that. So this is an option as a way to create some points that you're going to use in DA. Okay, we are going to jump over into DA now, into NCD. I'm going to pull up a couple of screens here. This is the DA model that we're going to be working with, and I've got actually 4 different systems that are here, so I'm going to turn these down to only the simple system that we're going to work on first. And let's see, I've already got this built. So we go into build, logic DA. So that's how we get to DA logic. That opens up this port. I've got this set up for 20 seconds. Each one of the devices that exist in your NCD configuration file are going to be listed under the master device list. Now for this bigger system that I had over here with 20 or so devices in it, those I have modeled in another master port. So this might be a serial port that you're talking to line devices through radio. It might not. This is a network port that I have where I'm talking IP to each one of these devices. The configuration that I have here in my lab, I have Orion LX that I am running all of the DA demo on. I have an LXM sitting right next to it. It's on the same network, but that is mimicking all of the devices in the field. So I have the LXM set up so that when I send a control from DA out to recloser R1, that recloser R1 is actually being switched in my simulator that I have built into the LXM. So when we do these demos, we're going to actually see real-time live executions of the DA system. So all of my devices are listed here and modeled so that I have recloser 1 is an SEL recloser with a particular type of control. I go to those inputs, and these are all of the inputs modeled exactly the same points that you would for a real line recloser. So that's what's modeled in this system. We have to first tell DA is over on this side. This is the master over here. So I'm going to build this model of this feeder. It's going to start with feeder breaker F1. I've got feeder breaker F2 over here, recloser 1, recloser 2, and a switch in the middle. So through my list, I can find feeder 1. Here's feeder 1, and I am going to, you can define it as normally open or normally closed. So right now I'm going to accept this as being normally open, and in DA, because a lot of the DA systems might be using a less reliable communication method such as radio, you can actually have a number of retries for a DA operation. That's a little bit different than what you normally do with SCADA, but so if you send a close to a line recloser out here in the middle of the blizzard, maybe the first command that goes out doesn't trip that recloser. So you wait for a period of time, and I'm going to say that period of time is going to be 5 seconds. Accept it, and it will put this over here. Now I already had feeder 1 set up as normally closed. You can define it as normally closed with this checkbox, or you can define it as normally open. So each one of the devices that's over here, you can define the normal state as open or closed, and you can actually define both of them. Just don't use them interchangeably because they are different. Remember, from the beginning I said that you can only operate a device from its normal position to its abnormal position. So this occurrence of feeder 1, I can only open this device through DA, but I won't be able to close it. If I had to close it, I would use this one because it's normally open, and now I can send a close command in DA and operate that device. So that's building up the list of devices you're going to use. That list propagates over to the available DA devices on the zones. And now we're going to start building the zones of what does the feeder look like. So zone 1 right here goes from feeder 1 to recloser 1. You create that new device or new zone, give it a name, pull the devices over into here, and you identify which device is the head end. So I've already got the first 2 zones defined. Let's do the next 2 zones. So the next one I'm going to do is zone 3 is going to be a new zone, and we are going to go from R2 to S1. I'm going to pull R2 over here and S1 over here. These are the devices that define the boundaries of that zone. And once these devices are in this device list, those will be listed under the head devices, and I can choose which is the normal source coming into this zone. It's going to be the closed device going into that zone and accept it. I'm going to add another new zone from feeder F2 to R2, and you can name this anything you want. You are not limited to using this naming convention that I just used right here. But I pull over those devices that are going to be here. I can pull them in any order. So I've got, I brought in F2 second, even though F2 is going to be my head end. Makes no difference. Save that. These other options that are down here, com fail, you have some controls here to do the unusual. For this instance here, we're not doing the unusual. So the default values that are here are generally going to be good for you 95% of the time. When we get into the later part of the demo that is going to be thinking outside the box, then that is going to use some of these features. And we'll just leave it at that for right now. Okay, now we go to the inputs. We've got all four of our zones. We have 1, 2, 3, 4 zones that are part of this feeder. Going to go into our inputs, and if you imagine that there is a dark black line right down through the middle here, what's above are the fault detection and the reclose coordination. This is what I call the fault inputs and the reclose inputs for the device. What defines a fault? What defines that we have a problem in this zone with feeder F1 being at the head end of that zone? Now, feeder F1 being at the head end is at zone feeder 1 R1, that's here. So that's looking specifically at these inputs. What we have from this list over here, we can go to the DA devices, and here are the inputs for those devices. Now that's all 100 some odd or 20 some odd devices that are there. You can sort it alphabetically. I'm looking for 51s, and here we go. So here's 51A. Make sure that you pick the correct device. Okay, I've got 51A, but I've got it here for 12 different feeder breakers. So I would take that, using the arrow going across, bringing it across here. So here's my fault indicators. This is my lockout. Let's go to feeder 2. I've got fault indicators here that I already brought across. Let's find the 79 LO. That for feeder 2, because I'm doing feeder 2 now, and simply bring it into the lockout. So when I have at least one of these points high and I get a lockout, then I'll trigger the DA operations that are being sequenced for feeder 2. In this case, I am going to add another input that we'll come back and talk about a little bit later, just a minute, and it's called shot. Let's see, where's shot? There it is. And I'm going to put that into the shot input. When we do the demo over on the screen over here, we can see how that works. Okay. Let's hold off on these for a second. Let's go back to feeder 1. Let's going to start with a demo of feeder 1. So what we have, I'm going to bring one of these screens over. This dark black screen is echoing what the simulator is doing right now. So I've got the system is normally set. I'm going to turn it into auto to enable the system. and all of those M's got changed to an A. The R, I can put a device into local, or I can put it into remote, so supervisory is off. If I put it in remote, supervisory is on. Okay, so let's see what happens when we initiate a fault here. And you'll see that this breaker is opening, closing. The light blue line is an indication of voltage is present, so there's no voltage here right now. This dark blue window, you can see what it's doing in the simulator. It says it had a fault. It's going through reclosing. If you looked at the timestamps that were here, it's telling you in real time, this is what's happening. You saw that X pop up here. DA had identified that that was the location of the fault, opened up this recloser, closed this switch. Okay, so let's look at the zone steps of what actually happened here. Whoops. Or let's see what we would have to do to make that work. Okay, I didn't finish configuring this yet. So we have outputs for the feeder 1, 2, and feeder 1. We are going to go to our DA devices again. We're going to sort this by alphabetically so we can find our points. And here's the trip and close point for that device. DA, or the DA logic, this is intended to be a trip close pair. So you would be using the same point to go into both of these. I believe that we have some intentions to be able to make a change that these can become separate trip close pairs, separate trip close points. If you do have a device that has discrete trip and close points, you may have to write a little bit of Visual Basic or Lua to combine those into a trip close pair. Very, very simple code to do. Okay, so for zones, what we did right here, we had a fault on feeder R1. We're going to define those zones. The first thing that we did when the fault is here, protection already opened up feeder F1, and we had a fault on zone 1. So that's going to be the steps that we're looking at is for feeder F1 to R1, that's this zone. What are we going to do? The first thing we're going to do is we're going to open up recloser R1. So we are going to find the normally closed recloser, and we're going to define that at the open DA device. The next step is going to be close the normally open switch 1. And that is the extent of all that needs to be done on this device. Okay? For feeder R2 or zone 2, if there was a fault here, we would protection would open recloser R1. Switch 1 is already open. We're not going to bridge anything. So there are no steps associated with R1 to S1. On feeder 2 to R1, if we have that, we're going to create some new steps. We will open up R2, and we are going to close S1. So it's just the opposite direction. Let's reset this system. And on our inputs, let's take a look what happens with these safety interlocks, because this is really the core of what makes NovaTech DA logic different than everybody else, is these safety interlocks. So if we had a device in local. Okay, let's put the recloser 1 in local, and we're going to do that same fault. Okay, this window here, I'm viewing the communications on DA logic. DA logic is port number 4. So this is going to echo what DA logic in the Orion is doing. Where, whoops, this window was showing what's going on in the simulator. Let's not use that one as confusion right now. So we're going to put this window here. And for that same fault that we had on feeder 1, let's initiate that test. And we will see step by step that we have a fault coming on the system. And it will say that it identified a fault in zone 1 in just a minute. Okay, it's going through the reclose, got the lockout, and it says reclose its head-end device at device 1, F1. So F1 normally closed, detected a fault in its zone. So it identified that the fault is here, and it wants to execute those switching steps. That was open here, close there. But as it analyzes the system, it comes to device 12, recloser R1, and it says it's not in normal mode. So because it's not in a normal mode, it cannot operate that. So it was in local. DA is now done. It did not switch anything. We just have a dead feeder. And that's exactly what you would want it to do, because you would have to open here before you can bridge at that point. Another thing that's very important is to know that this condition is not hanging up in the system. So I'm putting that back into remote. We see that zone 2 has gone back into normal down here, but DA is not trying to kick off the rest of the DA switching sequence. It had a one-time shot of doing that. It determined that the conditions were not right. It could not operate that device, so it flushed it out of the system, and it's not sitting there as a hidden condition that is going to catch somebody when you go back to that recloser and put it back into remote. Okay. The other, let's reset the system again. Okay, that will operate these devices back to normal. We see that zone 1, DA1 here, has now been analyzed, and it goes back to a normal state. That's all being logged inside the DA log. And if we put this device into local, instead of the recloser, and we're going to do that same fault again. Okay. It will go through the same analysis, exactly the same fault. Okay, we reached lockout, so now we have a fault indicator. We have the lockout indicator. It identified the fault as being here. It's going to send and isolate to recloser 1. This device, switch 1, is still in local, so this recloser 1 goes into limited mode. It's not in an abnormal state. It's because it is in auto. It was normally closed. It was in remote did not have a hotline tag set, so it wasn't blocked in any way. But being that it's a limited mode, we can open this device but not close it. So by putting the switch in limited mode, it was not able to close here to restore back to that fault because of the rules of DA, but the recloser was able to operate. Okay, so there's a demonstration of the safety interlocks and how everything is being operated there. I'm going to reset the system and move that local one more place. Okay. And if I put local over here, okay, now this system over here is not abnormal in any way. We have everything is auto, remote, all these devices, but thinking ahead now, this device is in local. All of the devices that are on the zone on both sides of it are going to be put into limited. Limited says that you can open, but you cannot close. So even though this device is in local, for safety purposes, there's crew working over in here. Any device can be opened, but it cannot be closed. This device should be blocked and not be able to restore for the safety of your work crews. Again, same fault. Going through reclosing, we got our lockout. Here's the fault going to be identified. We'll open up here. The next step, step 2, or actually step 1, restore, says restore is not permitted. And it's logged in the DA log, so when somebody says, why didn't it work? You have documentation of it's intended to do that. That's a safety feature to keep your people safe. Okay, let's reset the system one more time. Okay, the other thing that I want to show on this system here is this trip to lockout. We had on the inputs for feeder 2, put that shot indicator in here. That is a trigger to allow DA to operate faster than it otherwise normally would. If you have customers that are sensitive to momentaries and you want to restore power as quickly as possible, then you would use this feature, okay? I just want to put a fault over on, whoops, let's put that back into remote so everything is reset. And on zone 4, we're going to initiate the same kind of fault that we had before, just so that we see, I'm going to clear that, just so that we can see the operation that would normally be done for this fault. We have it programmed the same ways we had for feeder 1. Okay, so there, it's all done, isolated the fault, bridged over here. We have this shot number 1 programmed into the shot input. What that does is it says, don't wait for the head-end device to reach lockout before you start switching. Start switching right away. And then if the feeder never does reach lockout, put it back where it came from. So I'm going to switch the system from trip to lockout to a momentary. And just so that we don't get confused over here, I'm going to clear that window. And let's do that same fault over again. I'm going to initiate this test. Same kind of test that we saw before. Okay. Now we're going to see this go through its reclose cycle. And as soon as that happens, we're already identifying the fault before this goes to lockout. DA starts, opens up the recloser 2, closes at switch 1. Any second now. Okay. That didn't. Okay. The HMI lagged a little bit, but let me explain what happened here. Okay. It did open here and close there, but then within the 20-second time that we were analyzing, this lockout never came in. So then what it does is it does a closed switch transition back to its original configuration. So it closed switch 2 or recloser 2, and we were tied, and followed by opening this to put it back. This fault looks like it's being hung up in here, but it's actually a wait time of like a full minute after the DA event is done before it lets go of that. So it just cleared the whole thing. I did not do anything to make that clear. It did it on its own. Okay, so that is probably the kind of thing that would be 90% of the DA that you're going to do. Now you're going to have much more complex feeders than this. So let's take a look at the next feeder situation. Whoops, click that one twice. Let's take a look at this feeder, and I am going to pull up a different model. Okay, this is actually the full model of the system that we're working on. So we're looking at system DA2 now. And I'm going to clear that just so that when we do this fault over here, we have the system is auto everywhere. Everybody is in local. And for a fault that occurs in section E here, feeder 7 is going to trip to lockout. The whole feeder goes dead. It identifies where the fault is, just like we did before, and it will start switching when the did I do something? Initiate that test. Oh, I had it on momentary, so never reached lockout. Okay, now with that triggered, and I meant to do that. So if the feeder was in lockout, you wouldn't want DA. If the feeder never went to lockout, you wouldn't want DA to switch anything. That was a valid test. Good for me. Okay, so now this is in lockout, and since I put it on lockout, we're going to do that test again. Sorry about that. Okay, here we're going to see this go to lockout. Now that we have lockout, it's going to locate that the fault was in that location, open up recloser 8, switch to switch 5, and restore power from feeder F8. All right? But how about if the source at feeder 8 did not exist? So let's reset the system. and I am going to simply open up feeder 8 for whatever reason. It could be that we just needed to take a feeder outage, okay, for what, but system is all still in auto. If we put a fault here, normally we would want to switch at S5, but S5 is not available with voltage on the other side. So when it goes through the analysis of this, it has an alternative switching point at switch 6 that it will use to restore DA or restore the power to this feeder at an alternate port. So here's the fault has been identified. It's sending a restore to switch 6, and with switch 6, it is closed all the way through here, and it did operate correctly. Okay, now how is that done? That sometimes it goes to switch 5, sometimes it goes to switch 6. That is done using an advanced not exactly advanced, but a higher level of DA. Okay, so for feeder section DA2, that's the system we're looking at, and for a fault on zone E, that's here, the first step that it's going to do is open up recloser R8, followed by close at switch 5, okay? But then you see that there's another little piece that's written here called a close verification function. And what the close verification function says, before you execute this close, check the logic that I have in here to see if that's permitted. If you take a look at step 2, that's right after this, that is also going to open recloser 8, and this closes switch 6. It also has a close verification function that says DA2 close S6. This one was closed S5. So there's two different verification functions that are going to allow or disallow that switch to be operated. So let's pop over to here and see what's going on. When we do a close verification function, this is a little piece of Lua. This is the whole thing right here that it is doing for this device. So when it gets down into the zone steps and it says execute DA2 close 5, DA2 close 5, it is looking at the logic that is coded in, right in this section here that says look at the voltage in zone G and zone H and see if there's voltage on the other side, and if there is, then go down through here and say, okay, there's voltage on the other side, permit that from device to operate, and it sends back a true from this logic. A true is received, it operates switch 6, or switch 5. On switch 6, it looks like exactly the same kind of logic. It's looking at under voltage on 5 and under voltage on each side of 5 in zone H and zone G, and giving a permit or block signal coming back. If you put those two side by side, they really are the same code, except that there's a few minor differences where this one is referencing switch 5, this one references switch 6. This one is going to return a value of true, this one's going to return a value of false. So even though it's executing the same logic, in this logic on the left, it returns a true if switch 5 is going to be executed, and it would turn a false if switch 5 was going to be executed. It would be the opposite if switch 6 was going to be executed. So only one of these logics programs would permit switch 5 or switch 6 to operate. Okay. And where do I want to go? I want to go back to this one and that one. Okay. Now let's turn on everything that we had turned off before. So we look at the whole system. The next level, okay, so that takes care of the control verification functions. The open verification function is very, very similar. It passes back a true or a false to allow that device to be open or closed. Okay, the next one that we want to take a look at is for a bus outage. This is still within the basic standard Flisser DA logic. So in this case, let's make sure that everything is fully reset. Okay, it is. In this case, we have a special zone that is set up. So I created a new zone called bus outage, and that would be for an outage at the substation. Connected to it is feeders 1, 3, 5, 7, and 9. So I have 1, 3, 5, 7, and 9 pulled over here, but there is no head-end device. When there is no head-end device, then it uses this loss of potential input on the feeder. So here's 1, 3, 5, 7, and 9, and they are all have a 27 element or an under voltage tied to the loss of potential. In order to identify a fault within this zone, that loss of potential input has to be true on all 5 of these devices. So we are going to get a loss of voltage at feeder 1, 3, 5, 7, and 9. That voltage is looking at the bus voltage, and when they all see a loss of voltage at the same time, that indicates that the condition is true, and whatever the zone steps are for the bus outage will be executed. Now, let's go ahead and execute it first so you can see what it does, and then we'll walk through how these steps are sequenced. So for a fault at zone S, which is the bus fault, I'm going to initiate this test. And because it's a different kind of a test, oh, I should be bringing up that window. Let's pop this up. Okay, so we have identified the bus outage, and step by step, it's executing the restoration of each one of these. Already, feeder 1 is restored, feeder 3 is restored, and it looks like we are just about done. Okay. So what it did was the DA, when it executes its DA steps, the early stuff that we did only had 1 or 2 steps. This one's got 9 steps. Step 1 opens up feeder breaker F1. Step 2 opens up feeder breaker F3, F5, F7, and F9 if you take a look at those open DA steps. DA will open all of the steps, or execute the open for all of the steps simultaneously if they are not sequenced. So you take a look at these. Step 1, it has a prerequisite step of 0, nothing, so there is no prerequisite step. Step 2, step 3, step 4, and step 5 all have no prerequisite steps. So all of those open commands will be executed simultaneously, and all of these breakers will open at once. That will separate the outage bus from the feeder, and then it will start looking at when the open step is confirmed as being complete. So it's going to communicate to F1, verify that it's open, then it will move down to the close step, and it will close switch 1. And it will do that based only on the actions and the state of feeder F1. And it will execute that. At that point, feeder F1 is bridged to feeder F2, and that feeder is restored. In step 2, do the same thing down through here. It will restore S2 to feeder F4, restore F5 to feeder F6. And now when we get to this feeder here, it still has that close verification function to say, am I going to restore here or am I going to restore there? So I can reuse that close verification function in other steps. It is simply logic that's going to be executed. This system down here is a little bit more complex. On step 5 for feeder 9, the first thing that we're going to do is open up this feeder. Then on step 6, that is sequenced after step 5, and we have to open up recloser R13. The reason is that we can't bridge everything that was tied together down to feeder F10, so we have to make some of that load isolated for a while and then bridge that later. So we are going to open up here, followed by, when this is complete, then we're going to close switch 8. And also, when this is confirmed, because that's what step 6 is, we're going to close switch 7. So by using these prerequisite steps, you can do a open and separate the close so that you can sequence multiples behind that same open. Multiple ways to do it, but that's one way to do it. And let's see, there was close and and then the alternate, the last step that we had here was back for feeder F7. If switch 5 was not available, we still have the alternate switching at switch 6 to be able to restore here. So that becomes the more complex bus outage that can be done in DA. I personally feel that it is, you should be cautious in doing any kind of automatic restoration from DA, and my reasoning for that is that typically DA is going to operate after an outage for something bad on the system. You know, a storm has come through, poles are broken, trees have fallen down, whatever the reason is. And you may have DA go ahead and do the switching to do an automatic restoration as much as possible. But during the repair, you might cut jumpers, you might open switches at that are not being automated, you know, so a manually operated line tension disconnect or something like that that is not being monitored by the DA. So if you were simply going to have the DA system restore itself based on voltage inputs or other triggers that say, okay, it looks like the fault has gone away, go ahead and put the system back, you potentially are restoring a system that's in an abnormal state and could put your crews in danger. So I do not recommend some kind of an automatic restoration of normal. The exception would be if you wanted to have an automatic switching schedule to put the system back to normal after you know that the crews are clear. So that would be a case, for example, after this bus outage. There were no outages or faults out on these feeders. If we reset that fault, and watch what's going on inside the DA logic window, it has a timer that is watching, okay, the system has gone back to normal. Then one by one, it opened up, closed the feeder, opened here. Close this feeder, open here. And you need to be extra careful in sequencing your restoration so that you don't, you know, if this was 3 different remote substations through here, you don't just go ahead and close everything, get circulating currents between multiple substations that would be occurring during the restoration. You have to make sure that you sequence your steps to be one at a time and controlled. In the restoration here, we're going to open up this switch. We still have to move the open point from R13 to S8. Now there are 3 different feeds coming through here, so make sure that we isolate it at switch 7 before we try to do anything with restoring that feeder back to where it needs to be. And then that was DA that did all of that switching to put the system back to normal. And again, through the DA outage restoration, what we had for this device was a special device, one that I created in sudomaster. And then if you take a look at the inputs for that device, there is special logic that, you know, we did in Logic Pack. Let's pull up Logic Pack here. And on the ands. Okay, so here was the bus outage return. We were looking at okay, the bus voltage was, here's the outage that occurred. Bus voltages came back everywhere. That became the input into the logic through here, and mapped it through with special testing or special logic that was configured in Logic Pack to make sure that the conditions were true to allow the DA to come back. Now that could also be done simply by a command from SCADA rather than the voltage came back, so that it could be more controlled as well. Okay, now we're going to move on to thinking outside the box here a bit. I'm going to pull this over and give me just a second to start the next screen. Okay, so thinking outside the box, DA was initially intended to be used for Flisser. And after we had a few years of experience doing Flisser, we found that the versatility of DA logic allowed you to go outside simply a fault indicator and a lockout to identify what a fault is or what a DA event is. And in this case, I had started putting in DA systems that were in adjacent substations. So here is a system of 4 substations, each one in a different color. The one that I'm going to demonstrate is the one that's in white in the center here. And there were some additional techniques that I came up with, one called cooperative DA and another one is conditional DA. So in the cooperative DA, this pink DA system was put in first, and there was some DA that was associated with recloser R9. So substation 1 running DA logic was operating recloser R9. At a later time, I put in some DA at substation B, and the feeder from substation A ended at recloser R9, and from substation B also ended at recloser 9 on the other side. So the original DA just used recloser R9 as being a normally open point with a blind bridging point, didn't know what was really going on the other side, and now substation B needed to do the same thing. But substation B was not able to talk to recloser 9 directly because the limitations of the recloser is it couldn't answer to 2 different masters. So came up with something called cooperative DA. So substation B is polling substation A saying, what's going on over at recloser 9? And whatever it knew of that recloser, it fed back to substation B so that both systems now were aware of what's going on. We could map a control at substation B to feed that over to substation A and pass it through to recloser 9 when substation B needed to operate it. So by setting up this cooperative DA system, both systems could operate recloser 9 as if it belonged to them, and both systems would be kept in sync with each other. The next part of the evolution of DA was conditional DA. So a typical distribution substation is going to be made up of 2 transformers that are to a bus with a split bus. So I have feeders being served off of one transformer, other feeders being served off of another transformer. No problem in operating the substation. When you have to take a transformer out of service, you close the bus tie, and these substation load limitations were limited to the emergency rating of the smaller of the 2 substation transformers. In this case, any one of those transformers could be taken out of service and carry the rest of the load. When you exceeded that, the typical approach in substation design would be, we need to get more capacity into the substation. You build a new substation, you replace transformers, you build new feeders, you move load to adjacent substations, and that is all good, valid solutions to the problem, but they're all expensive. When we took a look at what the true problem was, we found that these graphs show each quarter for the year that we had only one day for a very short period of time in the middle of winter, probably some abnormal switching, that we went over the load limit of a single transformer. Doesn't mean we had a problem in that substation. The load went over the limit, but we probably still had two healthy transformers, so the load was split. Same thing happened in the summertime, happened much more frequently or more often than in the summertime, that we had this high load, but again, we didn't have a problem unless we were operating the substation on a single transformer. So the conclusion was that if we put DA in to simply make the load go away when we have high load and we are operating on a single transformer, then we could defer the cost of expensive substation renovations and upgrades. Okay, and that's where I developed the load relief DA. So in this enhanced load relief DA, you are going to have to write some Lua or Visual Basic. You can do it either way. Not likely that you can get away with doing it all in Logic Pack, because there's some arithmetic involved that is a little bit awkward to do in Logic Pack. So in this case, we have zone 2 here that has 2000 kVA. Substation is allowed to carry 25,000 kVA, and it's already loaded up to 21,777. Okay, and at substation 2 over here, or actually substation 4, the allowed load limit is 15,000. It's carrying 10,000 kVA. If it were going to receive load from substation 1, it would be receiving this 2,000 kVA. 2,000 plus 10,000 is 12,000. That's less than 15,000. 2 healthy transformers. Everything's fine. Go ahead and transfer the load as needed, is the message that we send back from substation 4 to substation 1. So we establish a communication link that says what is going to transpire. So here's the way it's done. There's only 2 pieces of information that's being exchanged to accomplish this. So at substation 1, we have 2,000 kVA. We put that into a slave port that is being read from the remote substation at substation 4. So this is the load that I'm going to send. It's received over here as load to receive, and then substation 4 evaluates that and says, I can handle that load, ready to receive. It puts its message of ready to receive out on the return message on its slave port that goes back and being read as substation 1. Okay, so this is a master port. This is a slave port. Each substation is going to have a slave that's being read by the master at the other side. The slave is going to say how much I intend to send, and then it receives back a message that it's ready to receive or it's not. In the other direction, we have this 5,000 kVA that's being sent from substation 4 to substation 1, being received as this is how much potentially I might send you. And the evaluation in the Lua at substation 1 adds that and says, okay, that if you sent me that, I would be over my allowable load. And in this instance, the substation was in a transformer overload or a transformer, not overload. It's a transfer situation. Okay, so one transformer is out, the other two transformers carrying all the load. So that's what we had going on through here. And so with that, we are over the allowable limit, and we are in a transfer situation. The ready to receive message that goes back is false. It says, no, you cannot send it. So the message that is being received from substation 1 at substation 4 is saying, no, do not transfer that. Okay, so let's pop up. Oh, let's see. We're going to bring this over here. And that one over there. We're going to watch the logic again on DA logic. So in this one, oops. Okay, the zone steps for load transfer 1 is actually very simple. So that the load transfer 1 is going to be on feeder 1. It's going to open up recloser 11. Okay, down here. It's going to open up recloser 11. And step 2 is going to be open up recloser 8. Now you'll notice in these steps, because it is load transfer, we don't want to create a momentary outage. So normally in your Flitzer application, you're going to have in the same zone step an open here with a close, and it will open when it gets confirmation that the open has occurred. It will move on to the close. In load relief, there is no outage. It's simply an overload that you are trying to alleviate a problem or potential problem that could be damaging. So you are going to do a close first, and it actually does tie two substations together. When I first did this, there was a lot of concern that you were going to be tying substations together, and when we really analyzed the system and we got the input from system operators and people in the field, there was confidence that DA operated fast enough that the full transfer would be done before a tap changer on a transformer would respond to any circulating currents, so that we would break that at the open point before that DA would be done. So we would do a step 1 is to close first. Step 2 is open at this point. So let's go ahead and put this window back up and clear that. So right now we don't have a transfer condition. I'm going to open up that transformer and take it out, put the substation into a transfer condition. The load on the substation is 23,000 kVA We're allowed 25,000. Nothing is happening over here in DA. To say that we have a problem, I want to make sure I'm watching the right place. Okay. So now we're going to increase the load here. The load goes up to 5,000. And at that point, we have 25,000 kVA. We are not greater than this, so everything is still fine. If we now increase this to 3001, then the calculated load at the substation is greater than the allowable load. DA will then kick off, and it starts to analyze the system. The DA that I've put in here is being evaluated on a timer, and so it will have 3 potential zones that it could transfer, 1, 2, 3, but it will only take them one at a time. And in this case, it's gathering all of the information. DA load relief is going to operate a little slower than other DA. There we closed at recloser 11, opened up at recloser 8. That 5,000 kVA has now transferred. Total substation load is 20,001. It's below the load relief, and DA stops. If we transfer the substation back to normal, the transfer condition will go away, and everybody's happy. Okay. If we increase the load now to be something above 25,000, we have high load. Again, DA is doing nothing. So it is evaluating the DA. We just saw that flip through here, but no DA is starting because there is no transfer condition. Now we go back into the substation transfer. And we have both the transfer and the high load relief condition kicks off. Normally it would want to do stage 1 over here, but it's already gone. So in the 20 seconds that it's evaluating the system, it's looking at these, and they can be prioritized in the way you write your Lua, that this is priority 1. I believe this one is 2 and this one is nope, got it backwards. This one was 2, and it transferred 9,000 kVA, and again we're back to an acceptable condition. So that's how load relief DA is going to work. Let's go back to, let's take a look at what is happening inside Lua here. And I want to go to so down in here I have some code written as a high load timer that runs every few seconds, and it's taking a look at how much load is on transformer 1, transformer 2. This is half of the DA, or the conditions. Then we have the ready to receive messages that are coming through, and down here we have each one of those 3 zones of DA. So we're looking at if we want to bridge to substation 2, bridge to substation 3, bridge to substation 4. It looks at them in this prioritized order, and when one of them becomes true, it says that's available, I have permission to transfer in that location, then it will set that true and execute the DA. Okay. The last thing that we want to take a look at is going to be this excuse me, I'm loading another system here. A more advanced flisser that is being executed without being able to access information out of the substations. For whatever reason, this was developed by another one of our engineers at NovaTech, Elton Beanstra. And in his application, the utility he came from, they had a rural system that they were not allowed to get information from the substation feeder breakers. So they implemented a DA system simply on a loss of voltage that occurs on the system. Whoops. And in this case, go there. Okay, in this case, the DA is going to, whoops, I clicked the wrong button, sorry. Okay, in this case, let's put it into auto. The whole system is in auto here, and we're going to just take an outage on the feeder. The DA is limited to these devices in here. So the feeder goes dead, and the logic in the feeder says, or in the DA logic is saying, let's take these one zone at a time and restore it back to where we can find voltage. So let's connect here. Okay, DA logic is already running in this case, and it restored this section at M. When section M got restored, voltage became available on the other side of recloser 13. That triggered the logic for DA switching in zone L. So it so the logic for switching this, it ended up finding the voltage through S7 and close 7 to restore here. When that became energized, then K was able to restore to the voltage that was there. It is not going to close to restore back to the feeder because it has no information about that feeder to know if F9 is open because somebody manually opened it, or is it a bus outage, or is there a fault downstream of this feeder. So when the recloser is looking back to here, because it can't get any information from that, it might close in on a fault that's downstream of feeder F9. So the loss of potential logic simply stops right here. So the DA is complete for what it can restore. I did it one step at a time. Let's close that one. We're going to open up the loss potential DA. And in that case, a lot of that logic was being done in LogicPack. If you take a look at what was being done in LogicPack, okay, so for example, for recloser 12 to operate, we're looking at the status of recloser 12 and the status of recloser 13 and 7 in order to make a decision that this zone is in a position where it can automatically be restored. Going to go over to DA logic in that case. And those zones are using some of these more complex options that you have here. Because we are analyzing the system basically after a loss of potential without a fault, the logic for this is looking at what are the downstream devices for restoring here to look if there was a fault on recloser 13. So right here we have this zone that we're talking about. No, I take it back, this zone. So we had switch 8 and switch 13. We have a head-end device is this special device that has the logic for the loss of voltage and what can be operated, what can't be. But there's a LogicPack type of operation that determines the conditions to kick that one off. Also in the LogicPack, when a zone is identified as all conditions are good, there's a voltage available to switch to. It's in order to control the sequence of the restoration. The delay feature in LogicPack is being used to delay each restoration by 20 seconds so that we don't get a large inrush of current during the restoration, and it's being picked up one piece at a time. So that concludes what I have for Flisser and for advanced distribution automation. And I will throw it back to Jeremy, and he can take it from here.
All right, awesome. Thank you very much, Russ. Let me jump back in here. I thank everybody for attending today. If you have questions, please let us know. If you want to look at, DA a little more in depth, we can definitely work with you on any of that. Just wanted to remind everybody, if you haven't signed up for our power support community, it's power.novatechautomation.com. That's where all of our past webinars the recordings are found. There's documentation, application notes, all sorts of stuff for both Orion and Bytronix products. So definitely sign up for that website. Just go there and hit the register button, and we'll get notified. And then we have a little work to do to add you to the system, so it's not instant, but we'll try to get it as fast as we can. And that's it. Thank you, Russ, and thank you to everybody, and we hope you have a great rest of your week. Thanks.